And again, it's my pleasure to introduce another group of soon-to-be graduates. Eric and John have been working this semester on a river simulator that we have down in the fluids lab. It's kind of neat. It's now a little bit more accurate and controllable than it was. Their project actually picks up where a former student, Dan Hampton from last fall, left off. And so I'll let them describe the problem and their solution.
Thank you all for coming today. I'm John Ethridge, and this is Eric Teeters. And like Dr. Field said, our project was to develop a flow controller for the river simulator. So first, we'd like to acknowledge Dr. Field for being our advisor, Dr. Hill, Dr. Pearson, Dr. Cuban, and Dr. Mitchell. We'd also like to acknowledge Dan Hampton because he started this project last semester. We'd also like to acknowledge Don Moore. So the river simulator is shown here in the bottom right, and there's a pump in this tank that pumps water up to the riverbed and it flows down. It drains through a drainage hole here and is filtered through this pool skimmer down into this reservoir, and then a tube connects it and flows it back to the pump. And this simulator is useful because you can observe fluvial geomorphology, you can examine currents and flow characteristics of water systems, and there are particles in this riverbed of different colors, and each color represents a different diameter. You can also recreate flood using historical flood data. So we'll run a video here real quick that shows some students and professors using this. So this just kind of shows the water flowing down. You can see the different colors of particles. And it looks like they're taking some measurements at different depths in this water system. And this video came from EM River, Lower River. They manufactured this simulator. So here's the simulator starting with no flow, and you can see how the water affects just the natural geography like that. And this is the river simulator. This is actually the EM4 model, and the EM3 model is what we have in the fluids lab. So the end problem was that there were inaccurate flow rates being entered, and there were two methods of controlling the flow at first. There was a flow controller that shipped with the simulator, and one of the flow controllers did not display what the flow rate was that was being entered to the user, and the other one was inaccurate. So the end solution was he developed a LabVIEW interface for precise inputs. And although he developed this interface, this is the method of control for the user. And this isn't very user-friendly because a typical user isn't going to know the conversion between voltage and flow rate. So our problem was to make this a little bit more user-friendly and to allow users to input time-varying flow rates and also recreate historical flood situations by being able to input or being able to enter flood values or flow values using an Excel sheet, and also improve the accuracy for these flow rates. So this is the electrical equipment that Dan used, and for Dan to be able to obtain accurate flow rates, he implemented a differential pressure sensor here. And this just measures the pressure difference across an orifice and then sends a voltage to this NI interface. And the NI interface then sends it to LabVIEW, where the user can see the flow rate that's being sent out. But our problem was that this equipment is placed under the riverbed that you saw in the original slide, and is exposed to foot traffic and water damage from people being in the lab. So as a project summary, we needed to develop a LabVIEW interface to allow the user to enter time-varied flow rates and historical flood data, and we also needed to design a controller to improve the accuracy of these flow rates. And lastly, we needed to implement an enclosure to protect the electrical equipment from foot traffic and water damage in the lab.
Okay, so our first objective was to develop a LabVIEW interface that allowed the user to apply a time-varied signal to the pump and allow water pressures to change. So a quick overview of how our program works. The user will enter their data into LabVIEW, and then LabVIEW takes that data, the flow rate, and displayed to the user to see how much water is flowing through the system at any given moment. We wanted to verify that LabVIEW was actually showing us what we believed it was showing us, so we attached an oscilloscope to the output terminals on the NI interface, and then sent a sinusoidal voltage signal through the NI interface, and compared what LabVIEw was showing us to what the oscilloscope was showing us. And we were able to see that LabVIEW was accurately displaying the voltages. And then we also wanted to verify that LabVIEW's flow rate to voltage conversion was correct, so we measured the water flow and verified that it was also correct. And so from this point on in development, we could just trust what LabVIEW was showing us, and we didn't have to worry about verification. So the first thing we wanted to do was allow the user to input a constant flow rate. And so on the dial up here, the user can select DC or constant, and then the user also needs to select the physical channels that the NI interface is attached to. And then an output dial also appears for DC, which allows the user to dial up how much water they would like to flow through the system. That's the only control available for constant flow rates. Then the user also has 4 sinusoidal or periodic flow rates that they can choose from, and the physical channels there as well. And for each of these, a different dial appears. For square wave, a duty cycle also appears, and offset, amplitude, and frequency appear for the other 3, and square wave as well. And these allow the user to more customize the voltage signal being sent to LabVIEW, so they can change certain parameters and change what they're actually doing with it. The last option was Excel, and this allows the user to input a Excel file into LabVIEW so it can be read, and also change the time delay for the steps between cells. So if the user wanted to do an hour-long simulation, then they don't have to have a cell for every single second. They can do it for every half minute or minute or however often they want to do it for. And that time delay is milliseconds right now. At the end of the iteration for Excel, it plots the input onto the XY graph on the left, and that is the input data. And then on the right side of all of these different cases is a graph that shows the output of the flow rate over time. At the top, it also shows the numerical output, and then for these periodic ones, it will show an amplitude and frequency output as well.
So our next objective was to design a controller to improve the accuracy of these flow rates. So to start the design, we created a Bode plot, which plotted the magnitude versus the frequency response of the system. And this system did not have an ideal model we could apply to it. An ideal model might have a slope of negative 20 decibels per decade. But as you can see, this slope does not reach that, or this plot does not reach that slope. So what we did was we implemented a compensator and then tuned it experimentally. And the type of compensator we implemented was a lead lag compensator. And this is the block that was used in LabVIEW to put in the block diagram. And the window here in the bottom right shows the parameters that we were able to change to tune this compensator. So the first set of parameters we tuned were the gain, lag time, and lead time. And the gain is used to determine how fast the system responds. And the higher the gain, the faster the system responds. But if your gain gets too high, the compensator will overshoot the value that you're trying to enter. And we also changed the lag time, and this helps reduce steady state error. And after changing these 2 parameters, the system was stable and accurate and had a fairly fast response time. So we didn't change the lead time, but this lead time can also be used to increase the system response time and stability. So here at the bottom, we have an overview of our block diagram, and we're going to zoom in and talk about some parts of this. So the first part are the inputs, and we have the input frequency, the offset, the input selector, and input amplitude. And these controls may or may not be apparent on the front panel depending on what type of input the user is using, but the input selector is a dial where the user can change between DC, Excel, or a sine wave. So after the user inputs this data, it then goes to a block like this, which simulates the signal and generates the signal to send. And this is just a block to generate a constant signal. And you can see the only parameter that's being changed is the offset. So after the signal is generated, it's sent to our compensator. And then from our compensator, it goes through 2 checks to check to make sure that the voltage is in between 0 volts and 5 volts, which were the range of voltages that this motor could operate within. So once the voltage goes to those checks, it goes to these 4 blocks, and these 4 blocks send the voltage as an output to the NI interface and then to the pump. So one of these blocks, you define the limits where we define a 0 and 5 again as a second check. And then we also have to define what is being sent, and this was an analog voltage, and the physical channel that's being sent on, which is just the port on the NI interface that the pump is connected to. So these 4 blocks are similar to the 4 we just saw, except these receive the voltage from the pressure sensor as an input. And again, you have to define the physical channel here. And this is the port that the pressure sensor is connected to on the NI interface. So once 5U receives that voltage from the pressure sensor, it goes through a calculation to change the voltage to a flow rate, and then it's plotted on the front panel that Eric has showed here. And this just creates an XY plot, and it shows the amplitude on the Y and the frequency on the X. So before implementing this controller, flow rates were only accurate from about 150 to 175 milliliters per second. And after we implemented this controller, they were accurate from 110 to 175 milliliters per second. And this may seem like a small increase, but the motor only operates between 80 and 175 milliliters per second. So it's actually increased the range by 40% of what active flow rates would be. And flow rates below 110 milliliters per second were still approximately 20 milliliters per second greater than what the user would enter. And this was acceptable because as the motor receives that voltage that it can start to operate at, it starts sputtering, and the flow rate that it's sending isn't very consistent.
Okay, so our last objective was to develop an enclosure for all the electrical equipment, because as this picture shows, all of the equipment was just mounted on the legs supporting the trough, and if water were to spill over the edge, it could damage the equipment severely, or if people are using the equipment and are right up next to it, they could be kicking the equipment, not realizing that it's down there, or forgetting that it's down there. And so we wanted to find some type of enclosure that was cheap and that would protect the equipment from water spillage or from foot traffic, and also had enough mounting space and ventilation so that the parts wouldn't overheat because they were going to be used for a long period of time. And so a couple of our options were to use a project case like the one shown here, or we thought about a computer case. And the project case would have been, the low range would have been around $200, and we would have had to develop the mounting inside the case all on our own using whatever we had available. Whereas a computer case we found for around $25 and already had mounting available inside of it and would be ventilated to allow parts to not overheat while still completely shielded on the top to protect from water spillage. And so after some measurement and research, we did discover that a computer case was going to be usable, so we went on ahead and used that. And you can see we put the power supplies all in there, and the NI is tucked away. And all the cables that the user will need to access to utilize the equipment stick out the front and are readily available, while all the cables that the user won't need to access stick out the back. So the equipment enclosure and shipping and handling was $32. And if you take, hypothetically, if the faculty got paid $100 an hour, there were 4 faculty members that helped us for a total of about 30 hours. Their cost would be around $3,000. 2 students at around $15 an hour for a total of about 300 hours would be $4,500. So our part of this project would have been approximately $7,500. And if you take that into account with what Dan did last semester, because he really laid the groundwork for what our project was able to do, the total cost of this project would be a little over $13,000. So what we did for our project was we developed a LabVIEW interface that was accurate for a greater flow range than previously, and also allowed the user to enter multiple different types of data to allow for time-varying flow rates. And then we also were able to protect the equipment from future wear and tear. We would recommend for future work that some type of filter be implemented at the end of the water tray, because the current system right now just uses this mesh netting here, which is a little too big, so it only catches the largest of the particles, and the smaller particles still go through and can easily clog the pump up. And so we discovered that the smallest size is about 0.05 millimeters, and so a mesh size of 420 microns should be sufficient enough to stop even the smallest particles and with still a lot of water to flow through. We would recommend for of sporadic, so it's really just unreliable. And for Excel spreadsheets, the data all has to be in the first column, and it must be saved as a .csv comma delimited file.
All right, questions? So you guys have a loading plot for your final design?
Hmm?
You have a loading magnitude plot for your final design, kind of show it one. I assume it was an open loop.
Yes, it was open loop. We tried to actually make it closed loop, but there was a syntax error with how we designed it. It would bring it back in as an array into our while loop that we had in LabVIEW, and it wouldn't actually send the data through until the while loop was completed, or the iteration had been completed, and so we weren't able to get that to work out.
So how did you get your loading plot for the one that you showed?
That was with the oscilloscope. We
We put in a sinusoidal input, and we kept the offset and the amplitude the same, except we changed the frequency, and we calculated the magnitude by the flow rate that was out over the voltage that we put in. And the only thing that we changed on that loading plot was the frequency of the sinusoidal input.
So did you try to do that with the controller
Implement.
in the loop?
No, we didn't create a voting plot with the controller. We just measured the flow rates off of the graph on the front panel LabVIEW versus the flow rates that were being entered.
So I just kind of want to tell you that time response to commands is not a feedback property. That can be taken care of outside the feedback loop. If you're interested in doing feedback control, you need to be telling us about bandwidth, gain over working band, stability margins, high frequency roll off. I don't know, did you talk about any of those, or?
Well, we didn't use any feedback from the pressure sensor in the controller. So, but really the only thing that we measured after implementing the controller was just the accuracy of the flow rate. We did have a bandwidth issue though when we used DAMs. We showed the 4 blocks that actually sent the task from LabVIEW to the NI interface. And LabVIEW has a DAC assistant, which is kind of like a data acquisition wizard that would find the channel automatically. And that did create a bandwidth issue. The program really slowed down and wasn't able to send and receive those voltages at the same time. So we went with the streamlined the 4 blocks, created the virtual task, and we were able to talk to the NI interface using those. That was really the only bandwidth issue that I think we had.
You may have already said this, but to what do you attribute the inaccuracy below 110 millimeters?
But the mechanics of just how a pump works, when it is operating at low flows, it's trying to push that water pressure through, and between revolutions of the pump, it can just kind of seep backwards through it, or just provide inconsistent pressures because it's operating so slowly.
On your case, how many wires do you have coming out of the case that run directly to other things? Did you think about cleaning that up and having it so wires would plug into the case instead of wires running out of the case?
Here.
This case?
Yes.
This was about as clean as we could get it with wires coming in and out, because the 2 wires on front have to be able to connect to both the pump and the NI interface, and the USB cable has to connect to the laptop or whatever computer you're using. And the wires that go out the back are the voltage wires that go to the pressure sensor. And so there really weren't many other cables that we could have kept inside the case.
Okay. Any other questions? All right, let's give them a hand.